second day in Chapter 4. Chapter 4, more integration, antiderivatives, and such. So let's start by looking at the relationship between a function and its derivative. So I've got this purple f prime of x graph that's sitting here. So if that's my f prime of x graph, we've done a whole lot of work here. Looks like my derivative looks like it's negative. So my f prime is negative in this interval, and then it becomes positive in this interval, and then it becomes negative again. Well, what happens if the derivative is negative? If the derivative is negative, then what happens with my function? Well, if my derivative is negative, then my function has to be decreasing. If my derivative is positive, my function's increasing. My derivative is negative, my function's decreasing again. So I have to have a function that's decreasing, then increasing, and decreasing. This derivative looks to be a parabola that's opening down, which means it's probably a negative x squared, which means my original function is probably a negative x cubed. So what have I got? So it looks like I'm going to have a relative minimum at this x value. I'm going to have a relative maximum at this x value. So let's just randomly put my minimum value here. Let's randomly put my maximum value here. And if I graph a cubic function that would fit that description, there is a potential f of x graph to go along with it. Now, is that the only one that we could possibly have? Well, no. Mr. Perkins, how did you know where to put the minimum? Because what if I would have wanted to put the minimum right here? Okay, if I would have wanted to put the minimum right here, my maximum would still have to be higher than that. So if I did graph this thing, is it possible that my f of x graph could have looked like that one? Yeah, absolutely. As long as it had a minimum when x was equal to, I don't know, whatever this x value is, this x value, it would have to have a minimum at the exact x value where this derivative function changes from negative to positive. It would have to have a maximum at the exact x value where the derivative changes from positive to negative. You've kind of got some play in how you create this graph. Well, what does that mean? So I'm taking care of this graph, so there's your little bit of a review. So now let's play around with the solution to a differential equation. What's a differential equation? Differential equation that you see in both of these things. What did I take the derivative of in order to get these derivatives? What was the original function that kind of begat the rest of these things? So general solutions show a rough graph. So here's my dy dx. We're going to do it both graphically and algebraically. So let's do it algebraically first. So here's my dy over dx. I'm going to start. I want to find my graph of y. I'm looking for y or f of x, whatever it is that you want to call it. So let's do our antiderivative. So my antiderivative of this thing, I'm going to start by separating my variables. So here's the dy on this side, and here's the quantity 2x minus 1 being multiplied by a dx. And if I now go through and I integrate this thing, or do the antiderivative of what I have, well, left side of this thing, what do I have? What would I have taken the derivative of in order to get a 1 if I was using y's? Well, this would have to be my y. Whoops, let's use red to make it match the colors we had. It'd have to be y. And on this side, what would I have taken the derivative of in order to get 2x? Well, I think that would be, let's see, add 1 to the power, divide by the new power. If you add 1 to the power, it's going to be x squared. If you divide 2x by a 2, you're going to end up with a 1x squared. What do you take the derivative of in order to get a minus 1? Well, that would be a minus x. And don't forget your c. Well, if that's the case, what does this red equation look like? So here's my antiderivative. I found this is my function that I would have taken the derivative of in order to get that dy dx equals 2x minus 1. Okay, well, what's this graph look like? Well, this red graph would look like a parabola, and it would be opening upward. Well, I'd have to complete the square in order to find the vertex. I don't want to do that. So let's come over and let's look at this graph. So here is this purple graph is my dy over dx is equal to 2x minus 1. Got it graphed. Has a slope of 2, has a y-intercept of negative 1. There's what it looks like. Well, now my red graph is supposed to be a parabola that's supposed to be opening up. Well, graphically, what does that mean? Well, we just said a second ago, according to the work that we did up here, wherever the purple graph hit the x-axis, the red graph would have to have a maximum or a minimum. So here, purple graph hits the x-axis. It looks like at about, let's call it 1/2. It might be a different decimal, but it looks like an x equals 1/2. Well, that would mean the red graph would have to have, well, let's see. Oh, purple graph is negative. Red graph would have to be decreasing. Purple graph becomes positive. Red graph would have to be increasing. What does this graph have? I would say that this graph would have to have a relative minimum at x equals 1/2. Is that the only place I could put it? Well, I could put it a lot of different places. I could put my minimum here as long as that minimum happened at the proper x value. Okay, so let's scroll down a little bit further. Look at part 3. Here we are with the exact same type of question. The difference is this one's supposed to pass through the point 1, 1. So the point 1, 1, where's the point 1, 1? The point 1, 1 is in the, let's use a color other than blue so it shows up a little bit differently. So at the point 1, 1 is right here. If the point 1, 1 is right there, I now have to have a function who passes through that point and has the minimum in the right spot. Well, as I'm glancing at this thing really quickly, I'm going to guess that this one is going to be a little higher. So let's see. Wait a minute. If I did this, I'm going to repeat this work. I would do this exact same thing again. Y is equal to x squared minus x plus my c. Well, now if it's got to pass through the point 1, 1, then everywhere I see an x, I'm going to put a 1. And everywhere I see a y, I'm going to put a 1. So 1 equals 1 squared minus 1 plus my c. What's that going to mean? My c is going to end up equal to 1. Well, what does this mean? That means that this graph that I'm messing around with, this particular solution, combining this information with this information, y is equal to x squared minus x plus 1 would be my particular solution that I'm looking for that would hit my green dot and have my minimum in the right spot. The black graph would be what we call a particular solution to the differential equation. Why is it particular? Because we have a specific c value. The red one is what we call a general solution. Why? Because it has some gray area in it. It has the c. The red ones can be wherever we want them to be. The black one has to be in the specific spot. It has to hit the right place so it passes through that particular value. And no, my red graphs and my black graphs are not perfect, but I hope you got the idea that one of them has to be drawn so that it hits that green dot, and the other ones can be drawn wherever they want as long as they have the minimum at x equals -1 or x equals positive 1/2. On the other side of this, here's solve the differential equation. I'm looking for solve the differential equation. What is the particular f of x? That's what I'm trying to figure out. I want the specific value that goes through f prime of 0 equals 1 and f of 0 equals 6. So let's start. If I want to find f prime of x, well, I'm going to do the antiderivative of this sine of x that was given to me with respect to x. Well, whose derivative is sine of x? The derivative of the opposite of cosine of x plus c. If you want to check that, derivative of cosine is the opposite of sine. Negative would give us a positive, would give us that black sine of x graph. Okay, well now if f of 0 is equal to 1, sorry, f prime of 0 is equal to 1, well that means everywhere I see an f prime of x, I'm going to put a 1. Everywhere I see an x, I'm going to put a 0. And I'm going to solve for my c. So so cosine of 0 is 1 with a negative on it, plus my c is equal to a 1. Move that over. My c value is going to be a 2. So now take this 2, put it in there. What is really my f prime of x equation? Opposite of cosine of x plus 2. Is that my answer? No, I'm supposed to come up with what f of x is equal to. What's the particular f of x? Well, if you want to find the f of x equation, you're going to take the antiderivative. I'm going to make this look lowercase. I'm going to take the antiderivative of my derivative function, my opposite cosine of x plus 2. So now we're going to take the antiderivative of that with respect to my x. So antiderivative of negative cosine of x. What do I take the derivative of in order to get negative cosine of x? Well, I think that's going to be negative sine of x. Let's check it. Derivative of sine is cosine, and then throw a negative along with it. What do I take the derivative of in order to get 2? Well, that would be 2x. And don't forget your c. Now, is the blue c going to be the same as the red c? No. And what you'll find in your when you look in the book or when you look on CalcChat or whatever, when you're doing things a little more rigorously than I am, they would call this red one the C1, and they would call this blue one the C2, so that people understand they're not the same thing. I will probably just do a generic C on a lot of things, and maybe that's not a habit I should be teaching people, but that's kind of how I'll do it. Well, now, according to the blue information, if f of 0 is equal to 6, then I'm going to put 6 in the place of f of x. I'm going to put 0 in the place of all the x's, and I'm going to solve for my blue c. Well, if I do that, sine of 0 is 0. 2 times 0, this c is going to end up to be a 6. So what is my function that I'm going to take the what is my differential equation in this problem? My f of x is equal to the opposite of sine of x plus 2x plus 6. And if you want to check your work, you'd take the derivative of the black one. You take the derivative of the black one, you're going to start by getting the red one. If you take the derivative of the red one, you're going to get all the way back up to that f double prime of x is equal to sine of x. And in this black equation, we'll pass through each of those conditions for each respective derivative. So here we are trying to find a particular f of x that fits the conditions that were set up for us in this problem.